Okay. Are we live? Hello? Hello? Uh-oh. Uh-oh. I think we're good to go here. Not receiving enough data, it might be buffering. Alright, hopefully this works out okay. Alright. So I don't know what's going on, why this is buffering. Hopefully it comes back. But we are going to come back and take a look at this problem. So what I would like to do is consider the solution here, and in particular, so there is a question of, okay, so Clojure math libraries or library. Let's try that. So mathematics with Clojure. Okay. Math numeric tower, math combinatorics, contrib libraries. Can we require in the REPL? So it doesn't say what this namespace is. Can we require? How do I require like Clojure add a library to the current namespace? And the REPL would be require. Loads libraries. Okay. So we could try to require this library, I guess. And maybe we can find like Clojure math libraries. This is contrib libraries. Interesting. Monads. Oh, yeah, I learned what monads are. I think I might make a video about monads just to explain them, because they're kind of simple but take a bit of sort of messing around with to really understand. Alright. The math libraries, maybe? Combinatorics, functions, and numeric tower. So what is this? There's some math in here. Core libraries. So let me see. In development, okay. Math functions, ceiling, floor, integer, round, square root, vars and functions, exponent, GCD, LCM. Okay. So not really a lot for the math library here in Clojure. Interesting. Looks like Clojure you're going to need to get outside libraries for the things that you're working on, things that you're interested in. Okay, so we can write an isPerfectSquare routine here. That's fine. So let's do that. Perfect square. And we're going to have a number. N. And we're going to say we're going to use binary search. So the way binary, so I have not coded binary search in I'll do it this way. I've not programmed binary search in Clojure at all, and I don't code it too often otherwise either. So binary search would look like is you have a start point, an end point, right, for your range, start and end. And what you're going to want to do is grab the midpoint between the start and end range, and you're going to check your condition. If your condition checks to be, if it's less than the start and end or greater than the midpoint rather, right, you check your condition on that midpoint. If it's either true or false, right, and usually implies either you got to check the lower end or the upper end. If you have this comparison with the midpoint. So in our case, we're checking to see three things. If we take this midpoint and square it, is it equal to our initial value, the value we began with? If it's equal, then this is a perfect square. We return true. If it's not equal, then we're going to want to recurse, but we're going to rebind the values that we're recursing on to the left side. So in our case, if we have this predicate we check, if it's false, it means that we're checking. I guess we're going to check if it's equal. If it's not equal, then we have it's either greater than or less than. If it's less than n, squaring it is less than n, we need to go to the right. If squaring it is greater than n, then we need to go to the left to use a smaller number. Right. And then going to the left, going to the right has different meaning. Going to the left means you recurse, but with your range is now the starting point stays the same, but the ending point becomes the midpoint, and does not need to include the midpoint because we already checked the midpoint directly. So you can do midpoint -1 for the end, and similarly to the right you do. Now these are inclusive, these endpoints. Similarly to the right, you would say the start becomes midpoint +1, and the end stays the same. And you're going to return when start is less than end. So at some point you'll end up looking at the same when start is equal to end, and you'll get the midpoint is I guess start it would be, and then you're going to have to either recurse to the left, recurse to the right, and at that point, when you rebind, you're going to be past the end point, or the end point will be it'll be past the starting point, and then you return. And then you return false at that point. So it's kind of interesting how this is going to look like. I wonder how other folks would program this in idiomatic Clojure. I don't know if this is going to be idiomatic the way we're going to do it. This is an example of, I think I mentioned in previous streams about, previous videos about fixed point iteration. This is an example of fixed point iteration where we don't actually know exactly how many iterations we're going to do. We can find an asymptotic bound on the number of iterations that we're going to do, but we don't know exactly how many iterations. So it's not quite idiomatic, I guess. It is still functional, although I'm not sure if we're using strictly functional things. Like this is kind of like controlled side effects. You know, it's very contextual. Like we have a full grasp of understanding of what the side effects are, but we are using side effects to manipulate this function because we're using a loop. We're using a while loop, changing the state of things. So I'm not sure if it's always possible to get away from using state. I guess how could you avoid using state here? I want to say something like basically your state is another parameter and it's a recursive function. So there is a kind of reduction going on here, right? You reduce that we want to perform, but I guess we can write kind of a binary search reduction where we have a predicate and then we have returns 3 different things depending on. We don't want to blow the stack here either, but we would return. That's kind of interesting. I guess it would be In this instance, the reduction could be done in such a way where one of the parameters could be the start and the end values rather than these being actual sequences. It could be start and end values, and then the thing about this though, like there's a couple things to say here, like I don't know if you can use a reduction for this exactly as the way we'd like to. I'm actually not sure. Maybe some kind of an anonymous function. It's a little different. Well, the inputs, the thing about reduction is that you're going to have the inputs are also the outputs, or like you input a problem and then the output is sort of the same problem after processing one value. So I guess the value that you'd be processing would be the midpoint each time, which could be calculated from the start and the end. And then the next problem you operate on is exactly the output range. What I think you'd want to do is manipulate. So you can submit the same, let's call it vector, every time, and these would be, I guess, values within the vector. Thinking about how it works with a binary search. Kind of a more generalizable Clojure expression for a binary search. It's like almost strictly functional. Because it is a kind of reduction, that's the thing. We want to take all of our functions or all of our manipulations and kind of reduce them to strictly functional forms of what we're doing, so that we're not using loops and recur too much. What we can do is so the input could be like a start and end values. So we could have, like, I'm thinking what would be the thing that we're returning and processing each time with respect to like what the reduction would be doing. So the reduction seems to be like there's some quote-unquote whatever, which is like a context and then a value, and then you return a new context, right? So what we would want is this, our original set of numbers that we're considering, which in this case is actually just a single number. It's not even a set of, well, there's a start and end number. It specifies a range. We don't actually, in this instance, have to return an array of numbers or anything like that, which would just be sort of another contextual parameter that's sort of static during the algorithm's execution. It would just be allocated. Wouldn't need to be reprocessed or reused in any way. It would be reused, but it wouldn't be regenerated at any point, which is good. So we don't need that in this instance, but we could just kind of add that as another, in our anonymous function would have this parameter, this extra parameter that would be kind of either built in or ingrained, or not really. But this function that we'd be using as applying in the reduction would not be needed. Like we wouldn't need to regenerate this thing multiple times. We can sort of bake that into our function, a reduction function. So what will change though is the start and end values. Those will change depending on what the function does, depending on what the predicate, if it's true or false. And so what we could do is continuously return the start and end range, and what I'm wondering is, if the start and end values, those two numbers, can continuously return those numbers. That would be functional, right? Because it'll return another two numbers, given that we bake in whatever range we're interested in right into that anonymous function. That would be functional, so we could actually reduce in that way. Now the question is, when does the reduction end? When does it stop? It's not really a reduction anymore, is it? If you have, you're not operating on a collection of midpoints, because the midpoint values themselves would change depending on what the result is. Interesting. You have to actually compute the midpoint. That's the next key. The next value does depend on the previous state. That's awkward. That is not functional, is it? No, not really. Oof. We're to ponder it now. How do we do this? How do we do this? All right, let me rename the stream to. We're gonna spend an hour trying to figure out. Let's see. Let's do it this way. How do we write binary search in a functional way? Let's learn Clojure. I was messing around with, got stuck trying to figure out what a quote-unquote strictly functional binary search might look like. All right. So, yeah, interesting. I don't have a good answer, man, because even if we so we could in theory have this reduction where the next key, so there's some range of values or some like set of values x that's baked right into our anonymous reduction function, and then the key we take, there's some key and there's an initial value as well. There's an initial value and the key value, and this key is supposed to come from a collection. Now that's kind of part of the issue, is that the values that we're getting from the key values, we don't know them, right? In fact, this is kind of necessarily not functional, maybe, because we change the state of the start and end range, the start and end values, to some other start and end range. It could be to the left or to the right, right? Split the range and take the left side, or split the range and take the right side. And then the key that we look at next is different from the key that we look at next is different from is you have two different choices to pick from. Now, I do think that the result of the algorithm at the end of it, you will always have the same, given the same inputs, you will always have the same output. So it is functional. The total algorithm is functional, but I would like the pieces in between to be functional as well. That's kind of the point of contention here. And how do we achieve that, right? How do we achieve binary search using strictly a composition of functions? Well, using reduce doesn't quite work either, because, like I said, we don't have a finite collection of keys to work with. Actually, the key is derived from this point in time the algorithm is executing. So that's kind of, maybe we could look up the answer. Maybe we could look up something that someone else has come up with about a functional, purely functional binary search. Functional data structures. Binary trees. This is also Haskell, I think. Or S#, excuse me. Still, it's not really what I'm looking for. I know that you can use search trees to emulate persistent data structures like vectors and hash maps and all that. That's not really, I mean, that's pretty cool, but that's not really what I'm curious about here. I'm trying to figure out how do you I get the feeling this is way more complicated than I would like it to be. Binary searches. Uh-oh. 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 Main Street Computer Software. Purely functional persistent binary trees. I'm actually not totally clear on how one would implement a binary tree in a persistent binary tree in something like Clojure. I don't really know what that would look like. It's a good question how that would be done. Purely functional ideal trees, common Lisp. Finger search tree. Finger tree nor display tree. Huh. Interesting. Finger trees. 1977. Interesting. Ephemeral. Yeah. So, you know, But they have trees, Clojure. They don't natively support, or they don't have a built-in support for binary trees. Persistent. Vectors, map sets, hash array map tries. Yeah, parallel computing. That's one of the reasons why I'm interested in Clojure, is for parallel computing. One day I want to do some machine learning stuff, and that's parallelization is kind of the way to go in the future. I need man. It's like a hash tree. Often used to implement a general purpose persistent map data structure. Hash array. Hash array map tries work similar to any generic tree in that they store nodes hierarchically and retrieve them by following a path down to a particular event element. The key difference is that hash array map try first uses a hash function transform path. Oh, okay, so this is basically like a tree. Okay, that's good. I need persistent trees. I wonder if, like, alright, how about just a tree? Let's just do binary, persistent binary tree, Clojure. Purely functional data structures in Clojure. Red black trees. Okay. Type of self-balancing binary search tree. Back when I first learned the balancing algorithm used in operations such as insert and delete, I remember it being a particularly tricky one. Red black trees are implemented destructively, meaning insertion deletions happen in place, so in imperative languages, a lot of node pointer manipulation floating around, making this algorithm error prone. As post, as the title implies, will deal with the functional implementation, which, besides simpler, is also persistent. Variant's big disadvantage of binary search trees is that they operate poorly on sorted data, with linear worst case pretty much becoming nothing more than a linked list. Red-black trees come in inserting and removing nodes, the tree balances itself, guaranteeing logarithmic time, satisfies two invariants. No red nodes can have red children. Every path from the root to an empty node contains the same number of black nodes. No red nodes can have red children. Every path from the root to an empty node contains the same number of black nodes. Interesting. Image below, taken from the book itself, concisely summarizes the four cases involved in these invariants, starting at the top and then moving counterclockwise. With this in mind, I set out to write the balance function in Clojure. Code in the functional version of a red-black tree, all pointer manipulation required in its destructive counterpart simply disappears, rendering the algorithm a lot simpler. Nevertheless, we're left with some complexity in the balance function around testing a node's color as well as its children and children's and grandchildren's. First attempt at writing it started like this. Make tree, color, color, left, left, value, value, right, right. Balance tree, case 1, and more. Extremely unhappy with this. A lot of boilerplate around bindings and tests. This is only the first case, but if you read Akasaki's implementation of the algorithm in ML, or Haskell, you'll quickly realize how concise and elegant it is. The main reason for that is pattern matching, something we don't have built in Clojure. Where Clojure is a Lisp and has a powerful macro system at its disposal, giving us core.match, pattern matching library for Clojure. Interesting. Using core match, I rewrote my balance function. Match tree, left, right, color, value, matrios tree. If you look closely at the patterns being matched, you'll see they cater for all 4 cases and allow for both matching and binding in the same expressions. Whoa. With only a little over double the size of a single case using the previous function, we now have a fully functioning balance implementation. This is better, but I wanted more. I really wanted to be able to write this. It's this. Whoa! Look at this. Black, red, red, black, red, red. Holy guacamole. Unfortunately, core.match doesn't support records protocols yet. However, while reading core.match's source code, I found a test that implemented the balance algorithm using a different way of representing a tree. A test that implemented the balance algorithm using a different way of representing a tree. You see, I went with the map approach because I like how you can ask for the specific keys that represent the parts of the tree, such as color, left, value, and right. But if you're happy with using positional elements in a vector to represent your tree, our balance function in Clojure becomes this. Wow, which is amazingly similar to the protocol's records version above. I guess one of the lessons here is that by carefully choosing the data structure to represent your problem, implementation can become substantially simpler. All code is on GitHub. Red-black specific section in this direct link. Also includes tests. Until next time. Amazing. Wow, 3 years ago they did this. That's amazing. That's really cool. Six years ago? Wow. Omits the ability to delete a node from the tree, and it's tricky to do this correctly, especially in a functional implementation. I prefer to teach AVL trees. Performance is competitive with red-black trees, and the invariant is more intuitive to understand and easier to code, especially in functional programming language. Unlike red-black trees, most students are able to work out how to implement deletion for an AVL on their own. I think treeps also be more elegant than red-black trees to implement. Although I can't say for sure because I personally haven't tried to do it. That's a good point. Should expand the post the removal implementation. Oh yeah, how do you remove a node then? It's good. It's a fair point. It's a fair point. Hey, caramba. Just messed myself here. I'll be right back. I'm gonna get some more water. Actually, I'm not going to go anywhere. So this is kind of interesting. So some folks have written implementations for at least red-black trees that are somewhat functional, although it's missing a the what's it called? It's missing something. Red-black trees that are functional. It's missing. Right, removal. It's missing removal, and then also AVL trees, I think, are probably good to write too. So, I guess the question is, does Clojure have binary trees that are persistent? And the answer is some folks have looked at that problem. And you can do AVL trees or you can do red-black trees. Definitely would be interesting to write. Look into a little bit more detail, spend some time, probably not on stream, on how do you implement the red-black tree in a persistent way, and then how do you also implement with the balance and the removal. Same thing for AVL trees. How do you do the same thing for those kinds of trees? That's interesting. It's also probably good to know that either offhand or at least how to, maybe you can put a library up there on the internet somewhere that you can be required. Put it somewhere in Clojures, I guess, something like that. So there is, maybe there's a Clojure somewhere for red-black trees and AVL trees. Let's see. It's gotta be. RP tree Clojures, yeah. Someone did. Clojure cookbook. Yeah, it looks like it was 3 years ago. And this post is already 6 years old. So, wow. Wow. Jeez Louise. Okay. Clojure script. Oh yeah, I don't, no, Clojure. Yeah, it's fine. Clojure match. Do you trust this though? 15 downloads. I don't know. I don't know if you can trust that. I don't know if you can trust that, man. Oh man. Okay, anyway. Cool. Neat. Very neat. I don't know what to do now though. Like just regular binary search. Like how do we do that functionally? It is declarative. It's not imperative though, and it avoids state and mutable data. Changes in state that do not depend on the function inputs. Understanding a program easier. I wonder if it matters. Church-Turing Thesis. Getting way off topic here now. Function on the natural numbers can be calculated by an effective method if and only if it is computable by a Turing machine. Thesis is named after Church and Turing. Precise definition of computable function. Mathematicians often use the informal term effectively calculable. Describe functions that are computable by paper and pencil methods. Formalize the notion of computability. So, function on the natural numbers can be calculated by an effective method if and only if it is computable by a Turing machine. It's possible to compute, I guess. Like, how do you define it though? Finite number of exact, finite instructions applied to a problem from its class. Always finishes after a finite number of steps, always produces a correct answer. Can be done by a human without any aids except writing materials. Instructions need only to be followed rigorously to succeed. In other words, it requires no ingenuity to succeed. Interesting. It's required that the method never returns a result as if it were an answer when the method is applied to a problem from outside its class. Requirement reduces the set of classes for which there is an effective method. Interesting. So ingenuity means that somehow you've figured something out while you're... So the idea, right, the computation is that, the idea is that, you know, it's not a human that's going to be executing these things, it's going to be a machine, so it's going to be very precise instructions, and even the instructions of like what other instructions you might use has a precise definition, right? There's even sort of a meta understanding of the instructions that, like, even if there were instructions to be injected into the algorithm, those instructions would have a finite set of instructions to determine what instructions would be it'd be calculable what those instructions are. Right? You don't need some ingenuity, some divine inspiration, or anything like that to change what steps you take in order to always be correct and always finish. Yeah, which is kind of an interesting addition, I think. But okay. It's Church-Turing is that functions are calculated if and only if they're computable by a Turing machine. Cool. Is there something even greater than the Turing machine? More potent? Right, in the automata theory, classes of automata. I'm wondering if there's a class of automata that's greater than a Turing machine. I wonder. Anyway, let's not get off the topic too much here. We're trying to figure out how do we implement, can we implement binary search in Clojure. Is that a thing? Is that a thing? Is that possible? I wonder. I wonder. Even just this binary search, you know, even more specific binary search, not a general binary search, but just on this particular problem. In a strictly functional way, I don't think we can. I don't think we can because it's not a. We can't use recur, or we can't use reduce the way that we might want to use reduce. That particular function doesn't really work like that because the collection of keys that we're working with changes depending on the state. So maybe well, we can definitely do this tail optimization thing. You know, rebind these symbols each time we loop and binary search iteratively. Yeah, we can do that, but so I'm kind of wondering if we rebind, we write our if statement. If the way if works in Clojure is a little different from other languages, like if we have this if statement and rebind the start and end values and then recur with those rebindings, I wonder if we need to have a separate recur at each point, because I want to have recur, it's supposed to be the last line that occurs in this loop. But I guess we got two recur statements within the if one direction recur this way and the other direction recur the other way. I guess it's fine, I suppose. I don't know. Excuse me. Well, anyway, I don't know. I don't know how I would do a purely functional binary search. I know how I would emulate an iterative search, binary search, but no, I don't really have a good answer for how I would perform the binary search in a purely functional way. It doesn't use like this loop structure, because I don't know the number of steps. I know it's a finite number of steps, but I don't know. It's impossible to know ahead of time how many steps you'll need. It's impossible to know which keys you'll reduce on. Without actually executing the computation. The step from state to state is, could maybe look at it that way. The state of the program is, it's a lot like following the path of a tree, and you're deciding which step to take down that tree depending on the current state. I'm not sure how you can model that otherwise. How do we model this thing? As like, the state is just a parameter, and so your function executes functionally. You could be given like a range and a predicate. I mean, this, it doesn't need to be general. The predicate we know is pretty clear in this instance, but a range and a predicate, and if depending on the predicate's value, you would return a different range. I mean, yeah, you could do this recursively. You're not really supposed to do things recursively in Clojure, though. You're supposed to use recur. Yeah, the function name also provides a recurrence point. I don't know. I got stuck on. I got tripped up on it. We've only got another minute here, so I would like to close this here, sort of end this here. Not end this, but kind of just write something that looks like this, I guess. So what we would do is recur on n, and we'll say n, and we'll have a start and end, right? And we'll say, could say something like define n perfect square helper n start end. And we'll say perfect square of n, right? And then we'll say return perfect square helper of n 0 n. And this is going to say let midpoint be start end plus divided by, say another like 10-15 minutes. Another 15 minutes just to program this part, and then we'll end the stream there. And then pick it up. You know, restart the stream as another section. So start divided by n divided by 2, and then we'll take I guess the floor of the ceiling, or the ceiling. Hopefully we can do this actually. Floor n. Can we even do this? Comment. Oh. Hold on. Okay, and we want require, so we can do just a test, I guess, right? Floor of 10.5, print line. Let's see what happens if we do this. Unable to resolve symbol floor. Okay, and then we can try, hopefully we can require as math, or math floor, and we can say require Clojure math numeric tower. Clojure math numeric tower. Hopefully that works. No. Class not found. Really? That's depressing. Use floor ceiling. Environment and samples, Clojure, algo monads, JSON, spec alpha. Doesn't have libraries. Additional libraries. Standard challenges. We don't have floor and ceiling. Math, maybe? Could we do that? So that didn't work. Can we do this? Please? Please! How do we not have the math library in there? Nice, it works. Okay, sweet. Sweet, so we can use math to access the, alright, environments. Math library. That's good. Okay, so, alright, let this midpoint be, and we'll use floor of this, right, that's fine. And then we're going to go ahead and say recur, it's going to happen here. We're going to say if if predicate, then recur, otherwise recur. Both cases recur. And this, maybe we could rebind this start and end. That's the thing I'm kind of, nah, that's fine. Okay. So if midpoint times midpoint square this midpoint, if you are equal to let's also do this. Yeah, that works too. We can say check midpoint times midpoint. If check is equal to n, then true. Right, simply return true. Else, we have another if. Right, and it's going to be check could be less than n. If check is less than n, then we want to recur on binding such that we're going to have the start stays the same, but instead of midpoint, we do midpoint minus 1. Otherwise, we have midpoint plus 1. And then the end stays the same. Just like so. Something like this. And this is what I think we need. Now, this isn't great. You know, I think I said that. Like, I don't particularly like this approach, but this may be the way to do it. I don't really know of a better way. Someone else has a better idea of how we can do binary search in Clojure. But yeah, so what this will do is you've got this end, start, end. You get this midpoint. You get this. This check is sort of our predicate, what we use for our predicate. You could do the predicate in a more sort of quote-unquote natural way, but in this instance, we just check if this midpoint squared is equal to n. If it's less than n, then you're going to recur here. Otherwise, you're going to recur here. And check is too small. That means actually it's the other way around. If check is too large, then you want to recurse to the left. If check is too small, then you want to recurse to the right. And then if you don't hit true, then you're eventually going to reach false. And that's what you return. Let binding. It's actually going to be, if it's true, yeah, if it's equal, then you return true. Otherwise, you return this part, which is another if statement, which is to recurse until it's true. There is one more piece here, and that's there's one more piece here, which is if start is less than end, then we're returning false. Otherwise, as we're doing this part. Yeah, I think that's fine. Maybe a better way to write this. So you get this, all right. Let's check perfect square here. This encryption of S. We can just run a few of these cases. Do 64, 4. We can do 100. So these should all be true, and then we'll say 50, 90, I don't know, 1,000. All right, let's try that. See how that goes. No standard out. Ooh. Okay. Oh, floor should be math floor, not just floor. Yeah. Math floor. The only spot we use it might be. Unable to resolve symbol midpoint -1. Oh, shucks. Yeah, I forgot about that. Decrement midpoint. And this is increment midpoint. Clojure is interesting. Definitely interesting. I like it. It's good. False, 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 false. 1, 2, 3, 4, 5, 6. Nice. You're kidding. Really? If start is, oh. Aha. Start is greater than end. Aha. Aha. There we go. False, 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 false. Well, that's not good. That's not good. Uh-oh. 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 Check is equal to n, return true. If check is greater than n, then you're going to say start is the same, but end point is going to be decrement midpoint. I think really should be if start is less than or equal to end. You want to do this, otherwise return false. And then if check is equal to n, then return true. Otherwise, if check is greater than n, then you got to recur on a smaller check, which should recur here, not the let. And if check is less than or equal to n, We already handled the equal case. It's less than or equal to n. And then could put this if inside here, I think. It doesn't really matter. And then we know it's less than n, and we need to go to increment the midpoint. These should all work, right? What's going on? What's going on? All false. I think we're missing. I think I know what the problem is. I've got to make it an integer. I think that's why it's comparing a double to an integer. It's not playing nicely. Oh, there we go. True, true, true. False, false, false. Neat. Yeah, not super like functional. You know, a lot of I guess side effects going on here. Doesn't really use. I don't really know how to do this otherwise though. Like, I just don't know. I haven't seen it. I have to like kind of figure it out then. But I wouldn't really know that. How to figure that. Like, it would take me time. I think quite a bit of time to figure out how should this be done. Really, really. Yeah. Humdrum, humdidum. Well, anyway, they give a bound on L. Yeah, oh yeah, they do 81. It's pretty small. Actually, if you're only looking at 81, you can make this even easier by using the nine perfect squares. Just check if the size of. It's very funny. You could just check if the 9 perfect squares. If it's in the set of the 9 perfect squares, this length of the string, the 9 perfect squares to consider, then that'll tell you whether or not it's a perfect square. Although this is an interesting exercise, getting to know that it's not always so simple to write it functionally, and that you may need to introduce some state manipulation, some mutability in your algorithms, in your code, in your program. Realizing that that's the truth. It's kind of a difficult realization, but uncomfortable realization, but I guess it is true. That, you know, this idea that, oh, you could always just use the state as a parameter, doesn't necessarily mean you can always, you know, just simply write it as a reduction, as a reduce. Every algorithm is reduce reduction. It's not true. It may be, I don't know, it may be possible to write a binary search as a strictly functional, like using strictly functional components. But I'm conflicted. I'm not certain about it, you know. I'm really like, I'm not sure, because you still end up with, you don't know the number of iterations that you're going to go through. It is like, binary search is a fixed point iteration. You may be able to prove a bound on the number of iterations, but you don't know exactly, and you don't actually know what decisions it's going to make until you decide to make it. So it's kind of, it's interesting. I'm not entirely sure how I would, like this interface definitely does present a functional kind of a function, but the components of this function are not necessarily functional. This one is, but then the let with a recur is not functional at all. or the if is not functional. Well, if is kind of functional, I guess. I don't know. Kind of conflicted about it. I feel like you can probably write this in a functional way. I just don't know it or don't see it at the moment. Let me stop complaining about it. Let me end the stream and say, all right, thank you for suffering through that with me. So now we both have a better sense of how one can write what a binary search might look like in Clojure. I don't think this is idiomatic Clojure though. It's binary search. I'm kind of surprised I didn't find anywhere like other people writing idiomatic Clojure, binary search in idiomatic Clojure. I was thinking I probably would come across that somewhere, but I did not see it. But here's, I guess, what it might look like. Not too bad to write, but definitely some points where you can trip up. You know, this floor and int is kind of necessary, and then kind of surprised the floor doesn't return an int. Yeah, I think this is okay. It's all right. Not great, but it's okay. Hopefully there's something better out there I'll come across at some point in the future. Yeah, we'll come back to the encryption later. We'll end stream here and then come back to it, and we'll look at sort of the quote-unquote the next episode will be how do we actually operate on this program once we know whether or not it's a perfect square that we're looking at. We can test the other two cases. Actually, we probably didn't even need to use a perfect square here to check if it's a perfect square. We probably could have just calculated this floor of the square root of L, convert it to an integer, and then say, okay, we have three options. We can do, call it x. We could do x times x. We can do x times x plus 1, or we can do x plus 1 times x plus 1. And you test all three of them and just take the smaller of the three that is also greater than L, greater than or equal to L. Could have done that as well. That doesn't require any of this stuff. A lot less thinking than is actually necessary. I don't think I'm even going to end up using this. It's kind of funny. That's just to determine what the row and column value should be. And then once you've determined what that is, then you can say, all right, we can do the rest of this, the quote unquote encryption. So yeah, we'll come back and do that. Man, keeping idiomatic C Clojure I think is kind of tricky, kind of difficult. So okay, so let's end the stream then.